Screen is visible.
Yes, sir, your screen is visible.
Now it should not be visible. Now it should also be not visible. Okay. Now,
Yes, sir.
so today we're going to study about the thermodynamic property of enthalpy. So in the previous classes we have discussed about the property internal energy, and in many cases, and in particular in the steady state steady flow processes that we will consider after finishing this, you will see that for control volume analysis, the property that is of particular interest will be enthalpy. So it is useful to sort of get around this concept. So let us again consider the same setup where you have a piston cylinder arrangement and there is some mass kept on top of the piston. So in this particular case, the pressure of the substance which is inside, that is constant. So it's a constant process. It's an isobaric process. Fine. So let us write down the first law for this particular control mass. Let us write down for this mass the first law. So it will be Q12 minus W12 is equal to U2 minus U1. Okay, now in this particular case, because the pressure is constant, the W12 will be integral of PdV from 1 to 2, and because it is constant, it will simply be P times V2 minus V1. Say due to some process, the volume goes from V1 to V2. We are having some process by which this change of volume occurs, and so the work done in that process, because it's isobaric, will be this, and consequently we can also write it as P2 V2 minus P1 V1, solely because P1 is equal to P2, because P1 is equal to P2. We can always write this as this. So now let us use this result. Let us use this particular result and plug it in over here. So we have U2 minus U1 is equal to Q12 minus P2 V2 minus P1 V1. Let us take this work terms on the left hand side. So U2 plus P2 V2 minus of U1 plus P1 V1 is equal to Q1. Okay, so the total heat transfer. So what can we conclude? We can conclude that the total heat transfer in the process in going from 1 to 2 is equal to the difference in this particular combination of terms, U plus PV. It is the difference between this in the final state and the initial state. Okay, so moreover, the heat transferred in going from 1 to 2 does not depend on the path taken. Okay, so Q12 obviously only depends on the final state and the initial state. There is no integration business going on. What does that mean? That this particular property, this particular combination of terms, is also a thermodynamic property. Okay, it is only a function of the state point. It is not dependent on the path. and therefore we can define the enthalpy capital H is equal to U plus PV. And if you divide everything by mass, uh, pardon me, yeah. So if you divide everything by mass, you can obtain the specific enthalpy. So the specific enthalpy will be specific internal energy plus pressure times the specific volume. Okay. So this is the expression for total enthalpy. This particular expression is the expression for the total enthalpy. This is the expression for the specific enthalpy. And in fact, let us verify whether this is true, whether this expression is true or not. And I mean, let me tell you also this, that in typical processes, when you're trying to measure, you actually arrive at the enthalpy of a given point. And so if you want to figure out what the internal energy is at that state, you actually do this, U equal to H minus PV. You actually do the reverse calculation. In our chronology, we first studied about internal energy and then we moved on to the enthalpy. But when you do experiments, you do the other way around. Okay, so the specific internal energy is calculated using the specific enthalpy and the pressure times the specific volume. So let me open Sontag and let us see whether this is true or not. I again do not have my calculator, it is at my quarter, but okay, I need to share my entire screen. Is it visible? It should be visible. Yeah.
Yes, sir.
So in all the tables, in the saturated water pressure entry table or the whatever tables you have, you will have at a given temperature an input for the specific volume, internal energy. Look, this is 195, 200. So if you go to the next page, so it's page number 676. If you go to page number 677, you again have 195, 200 and so on. But instead of having the specific volume and internal energy data, you have the enthalpy and the entropy data. So the entropy data we will come to when we cover chapter 7. So there's time for that. But for now, we are more concerned about enthalpy, that is H, and the internal energy. And look, in these books, and I have also done this many times subliminally, I mean, yes, specific volume is written as specific, but whenever they report internal energy in kilojoule per kg or the enthalpy in kilojoule per kg, it is assumed that you are going to understand this term as specific because it's per kg, it's not kilojoule. Okay, this total enthalpy is going to be in kilojoule, but the specific quantity is going to be in kilojoule per kilogram. With that out of the way, let me take a few screenshots. So let me take the enthalpy screenshot. Okay, instead of, yeah, we can do this. We can take this. So enthalpy, we put it over here, and internal energy, take this, grab it and put it over here. Okay, I don't have enough space, so I'll just push this over here. So this is fine. You're able to view whatever is written. Let's do the following. Let's do it at 200 degrees Celsius. Pressure is this. Internal energy of the liquid is this at 200. enthalpy of the liquid is this, and the specific volume of the liquid is this. So let's see whether U is equal to H minus P times V. So the right hand side will be H, which is 852.43, and so this is in kilojoule per kg. It is important to write this unit, minus pressure, which is 1553.8 kilopascal, 1553.8 kilopascal, times the specific volume, which is 0.001156 meter cube per kg. So essentially, because this unit is also kilojoule and this is kilopascal times meter cube per kg, so per kg matches out. So Pascal times meter cube is going to be technically joule, but you have a kilo over here. So kilopascal times meter cube becomes kilojoule. Do not be confused with the units. If in doubt, you do this calculation or you know. So what do we get over here? What is the amount? Let me open up the calculator. It's a very bad calculator.
The
Sir,
850.6.
850.6.
850.64.
Chalo, theek hai. Everyone has done it. And so we get U equal to 860.64. And what do you know? You also get 860.6. 860.64 or
Sir,
850.
850.
850.
850. Of course, it's
850.6.
852 minus something, so it has to be 850.64. What is the units? Once you say 850.64, you should also tell the unit. So it's going to be kilojoule per kg. And in many steam tables, so this is the steam table of Sontag. But there are many steam tables where they will completely not give you the internal energy data. It is expected that you will do it using enthalpy and pressure and volume. Okay, it is expected. If it is not given, you will do it using this data. But for all the problems that we're going to do, because it's from Sontag and Sontag is a very standardized steam table, it has a in the appendix B, so we don't need to worry about it all that much. And similarly, I have shown you data points in the saturated dome. I can also show you a data point in the superheated table. So we go to the superheated table. Let's say we focus on superheated steam at what is it? 2000 kilopascal. So this table is for superheated steam at 2000 kilopascal. So let's see whether this holds true. So let's say we are at 1000 degrees Celsius. The V is 2.29333, U is this and H is this. So let's do it. So we have U is equal to H, which is 4634.61 minus P, which is 2000, times specific volume, which is 0.29333. So what do you get? What do you obtain when you do this calculation?
Four zero four seven point nine five.
Well, no surprises over there, because this is also the same value that has been reported. Okay. What are the units? Kilojoule per kg.
Kilojoule per kg.
So everyone's getting this? Everyone has this?
Yes, sir. Yes,
Okay.
sir.
And this holds true for any kind of fluid. Okay, not just this. It's defined as this, so it has to hold true. Alright, so with the help of this, you can easily find out the amount of heat transferred when you have a constant pressure process. Now you may think, oh, wait, it's a very specialized process. It's just a constant pressure process. And is the enthalpy only useful for a constant pressure process? Enthalpy useful for constant pressure only? And the answer is no. Because once we have defined it as a property, once we've defined it as a state, as something which can help us identify a state point, we can use enthalpy in combination with anything. You can use enthalpy in combination with temperature, pressure, specific volume, entropy to obtain the state of a given point. It is not just like enthalpy is true only for a constant pressure process, because we have already seen that the combination U plus PV, this particular combination gives us a unique property which we have defined as the enthalpy, which helps in pinpointing where the state point is. It does not depend on path. That is a very useful thing to have, that the property under consideration should not depend on path. Otherwise, the property would be different. If I were to have a process which would be path dependent, so I cannot say that state point 2 is independent of whether I have gone there through path A or path B. Actually, the figure also won't look like this. If it were to be path dependent, then this would be state point 2 prime. So 2 and 2 prime would not coincide, but here, because it coincides, we can say that U plus PV, this combination, is independent of path, and correspondingly it can be used as another independent property to pinpoint the state of a substance. And hence it has been catalogued, it has been tabulated in the stream tables. Otherwise it would be pointless if it were to be dependent on something else. Okay guys, so there is a bit of reading assignment for everyone, and you must do this on your own. You have to activate your neurons. Okay, so the reading assignment will be 6th edition, Sontag. You have to read section 5.6, section 5.7. They are very, very small sections and they are very simple derivations, but regardless of that, you must read this. And once you read sections 5.6 and 5.7, you must do example 5.7. Okay, everyone must do it. All right, so we proceed in our journey, and I'm not doing it because it's very simple stuff, it's very elementary, and not everything has to be spoon-fed to you. People who are studying in IIT in particular, you must also go slightly out of your way to read these things on your own. All right, so we've studied the first law for a control mass, and everyone's feeling very happy about it. Very nice. So what was it? U2 minus U1 equal to Q12 minus W1. Yes, this gives us the first law for the control mass. And you may say that, okay, this is going from point 1 to point 2, but can we write this for a transient problem? Can we write this for a transient problem? And the answer is yes, it's simple. So I can write this as delta U. So there is a small caveat over here. Whenever I am writing the first law, it is not entirely true what I have written. There is a small assumption, and we have discussed this briefly. So just to refresh that. So the amount of heat added minus the amount of work done by the system will be the total change in energy of the system. So it will be U total at state 2 minus U total at state 1. I can write it as this. And what are the different components of U? What comprises U? U is comprised, U total rather. U total is comprised of the actual internal energy due to the molecular motion, plus the kinetic energy of the system, plus the potential energy of the system. And in all the examples that we have done, we have a closed chamber, you add heat and something happens. The kinetic energy and potential energy are not changing. This control mass suddenly does not start moving at some velocity. Neither is the height of the control mass changing. That is why we always sort of neglect this. And in this case, it is not neglected, it is identically zero. Okay? So, what it means is, suppose you want to analyze a car. It's a very nice car. And you say that there is some work done on the system, and so the velocity of the car increases. So then you can say that half mv square is the total energy at point 2, and it is due to some amount of heat addition to the system. But over in all the problems that we have considered so far, this total energy is comprised of only the internal energy due to molecular interactions. Is this clear? Whatever I just said, is this clear?
So the potential energy term is the external one, right? Not the internal one.
Internal potential energy and all that is all sort of accounted for in this molecular internal energy. So what would be an example of potential energy change? A simple problem. You have a pulley, it's connected to a mass, and you pull the string. So if this is the control mass, you're doing work on the system. So work done on the system. So what is, suppose I do 20 kilojoules on the system. So what is the sign? So W12 would be what for this control mass? Work is done on the system. Huh? It's at state 1 and it gets lifted to state 2. What is the work done on the system?
20
minus
kilos.
20.
So it will be minus 20 kilojoule because work done by the system is positive. Okay. So W12 will be negative. Is there any heat transfer in the problem?
No.
So there will be 0 Q12. So we have U2 total minus U1 total is equal to Q12 minus W12, which is going to be equal to 20 because minus W12 will be equal to minus of minus 20, which is 20. And in the first position, if I consider this as the reference energy, potential energy, so U1 total would be comprised of U plus kinetic energy at 2 plus potential energy at 2 minus internal energy at 1 plus kinetic energy at 1 plus potential energy at 1. But because the temperature of the system has not changed, there is no heat transfer, the temperature has not changed, whatever the contributions from the molecules of the solid block towards the internal energy, they will be equal. So U1 will be equal to U2, and so these two terms cancel out. Kinetic energy. Is there a kinetic energy? Suppose I do the work very slowly, so there is no appreciable change in velocity. At state 1 and state 2, there is no sort of appreciable velocity. State 1 is also stationary, state 2 is also stationary. Maybe in between it goes very slowly. But state 2 is stationary. So kinetic energy 2, kinetic energy 1 also vanish. Now you simply have potential energy at 2 minus potential energy at 1, which is equal to 20. But I'm saying that potential energy at 1 is at z equal to 0. And therefore this also becomes 0. So when the amount of the height raised is h, so what is the potential energy at point 2? Suppose the mass of the block is m and the acceleration due to gravity is g.
It's MGH.
MGH.
So mgh will be equal to 20. This is how you would do the problem. Okay. It's very simple, but in all the problems where you have these thermodynamic systems, there is some mass, you're compressing the piston. You see, there's not going to be a change in internal energy. There's not going to be a change in kinetic energy or potential energy. So you simply usually neglect it. Okay. So with that in mind, first law for a control mass was this. In the derivation of enthalpy, whatever U this was, it was only molecular internal energy. And the reason why it was molecular internal energy is clear. Because if kinetic energy, potential energy come into the picture, then it would not be a state property, it would become a path property. And the problem that we have defined, it's a piston where some substance is confined. There's obviously going to be no change in potential energy and kinetic energy. So in this particular derivation, this U was only the molecular energy. And you will see in many problems, you can neglect kinetic energy, potential energy. But we will also see in certain problems in the next chapter where kinetic energy will be important for things such as nozzles. There's some message. Okay, there's no message. Okay. All right. So the question was, how do we make a rate equation out of this? How do we make a transient equation out of this? We simply write down the law. So kinetic internal energy change plus kinetic energy change plus potential energy change is equal to the amount of heat transferred minus the amount of work done by the system. Then we divide everything by delta T and we take the limit delta T tends to 0. So you have essentially du dt, right, plus d kinetic energy dt plus d potential energy dt is equal to q dot, where q dot is dq dt, but because it's not a perfect integral, we can represent it as q dot, which is the rate of heat transfer. This is simply rate of heat transfer, nothing else. And dw dt will be w dot, that is rate of work done. So what is the rate of work done, commonly known as
Power.
power. Okay, so it's as simple as that. All right, let us move on to problems. No thermodynamics class is complete without doing certain problems. So let's see which problem we can do. Let me quickly unshare my screen first so that I can fetch the problems. Just give me a minute. So we are in chapter 5. So there's nothing complicated about chapter 5. I mean, in fact, there is nothing complicated about the entire subject. It's just if you don't do the problems, you will feel in the exam that, okay, this is some Hebrew thing going on. Let me share only the journal window. Okay. Here we have a problem. What is the problem? This is, what problem is this? Come on. 37. So this is problem 37 of Sontag. Okay, so problem number 37 from Sontag is a very simple problem, of course. So we have the problem statement over here. A cylinder fitted with a frictionless piston contains 2 kg of superheated refrigerant R134A vapor at 350 kilopascal, 100 degrees Celsius. The cylinder is now cooled so that R134A remains at constant pressure until it reaches a quality of 75%. The question is, calculate the heat transfer in the process. Let us draw a cartoon. This is a piston, and over here you have R134A. So in the cartoon we can write 2 kg R134A. State 1 is 350 kilopascal, 100 degrees Celsius, and this is superheated vapor. Then the cylinder is cooled, so state 2. So 1 to 2 you have cooling, and it remains at constant pressure. So this pressure is also 350 kilopascal until it reaches a quality of 75%. So X will be 0.75. The question is calculate the heat transfer in the process. First of all, is the problem clear?
Yes, sir.
Okay, so if the problem is clear, we will write down over here that this is the control mass, and we will immediately do what any sane person would do. What is that? What would any sane person do at this juncture?
Draw a graph.
Draw a tentative schematic for the process. Yes, so essentially draw a graph. Thankfully, no one said leave the class. So we will do what any sane person does. So where is point 1? Okay, not Venkat, not Anirudh Bajaj. This will be answered by Azmera Chandramani. Where is state point 1? Chandramani? Okay, is not there. Who else is there? Not Devik Agrawal. Devansh Srivastav. Okay, not there as well. Saili.
Yes, sir. So it is superheated, so it will be outside the dome.
So over here you mean
No, right side.
here.
Yeah.
So I will mark this as point 1. Now where will be point 2? In this PV diagram, where will be point 2?
Sir, it is said that constant pressure. So if we draw the isobar, then it will be at the same line.
So how will I draw the isobar?
From that one point, you can draw a horizontal line.
Very good. Very good. So this is the isobar, you mean?
Yes, sir.
And state point 2 will be where?
It will be inside the dome.
Very good. So this is state point 2. So now what should we do? We should also, I mean, just for our understanding, we should also draw it on a PV diagram. Just for our understanding, you don't need to do it. So Saili,
Yes, sir.
where is point 1?
Superheated again.
Somewhere here, is it?
We can
Now,
take it.
now where will be point 2?
Sir, it will be lower than point 1 and inside the dome.
Okay, you mean over here?
Yeah, I guess we can draw an isobar line, then it will be on the same line.
So how will the isobar look?
From niche se, like from the left side, you can take it up to the dome, then horizontal, and then from point 2 to point 1.
Point 2 to point 1. No, she said point 2 to point 1. So I will
नहीं
draw
नहीं 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 मतलब वो cover
this
करके
point.
हाँ.
So you should be more precise in your description.
Yes, sir. Sorry.
नहीं, that was quite funny. Anyway, so this is how the process looks like. Is it clear to everyone?
Yes, sir.
So this is first thing you must always do. I mean, just quickly draw it. I mean, we are spending some time to draw it, but ideally this should be done within like 20 seconds, what the process is. But you can spend some time on this. I mean, it is worth spending some time on this. So I will just take this. I'll just push it to the side because everyone gets it. And I will write over here that U2 minus U1 for this control mass will be equal to Q12 minus W12. Let us do it the old way. This is first law for control mass. Okay, so what is Q12? It is U2 minus U1 plus W12, and because it's a constant pressure process, okay, we can write this as U2 minus U1 time U2 minus U1 plus P times V2 minus V1. Or essentially, if I write this from the total internal energy, look, again I have assumed over here that the kinetic energy, potential energy is not going to change, so I have cancelled everything out. This is only the internal energy. So I can write this in terms of mass times the specific internal energy difference plus pressure times mass times the specific volume difference. So essentially it is mass times U2 minus U1 plus P times V2 minus V1. Okay, this is what it is. So let us see state 1. So 350 kilopascal, 100 degrees Celsius. So 350 kilopascal, 100 degrees Celsius, we need to go to Sontag. Okay, we need to go to Sontag and we need to go to which thing? R134A, right? So this is superheated water vapor. So we need to go to R134A. This is R12, R22, R22, R134A. We have properties of R134A. But the first point is what? The first point is superheated vapor, 350 kilopascal. So this is superheated R134A and this is the 300. Okay, now we have to do some stuff. So we have R134A, no doubt, but this is 300 kilopascal and we have 400 kilopascal. There is no entry for 350 kilopascal.
350, yes, sir.
So we must do that thing. And what was the temperature?
So 100 degrees.
100.
100 degrees Celsius. So we need to copy this. We will do it. I mean, I'll show you. I mean, there's no focus, no magic. And lastly, we will do what any other sane person would do. That is, do it using EAS. Okay, so state 1. I'll just write it down over here. It is 100 degrees Celsius, 350 kilopascal. So I don't want to spend time on this, so I will directly write down the thing in terms of enthalpy because we have just studied it today in the beginning of this class. So it is M U2 minus U1 plus P2 V2 minus P1 V1 because P1 is equal to P2. So this becomes M H2 minus H1. Okay, this is mass times the difference in specific enthalpy. This is what is Q12 going to be. So let us directly fetch the enthalpies. Let's not first evaluate U, then V and do that whole thing. Because we're doing it using table, we need to be fast. So we need to look up tables as minimum as possible. All right. So over here, 100 degrees Celsius. Okay, that's not the right color. 100 degrees Celsius. Enthalpy this, enthalpy this. And the only saving grace in this particular thing, right? What is the only saving grace?
That it's between.
Very good. That
Yes,
is
sir.
between,
It's average.
it's just the average. Very good. So you get it. So 300 kPa, 400. Otherwise, you have to do this. You have to write down 490.48, 489.52, and you are looking at 350 and question mark. H unknown you call it, or H1 you call it. So what is H1? It's something very close to 490, right? I mean, looking by this, it should. I mean, this
Sir,
is
it's exactly 490.
490. So it's 490 kilojoule per kg. Always remember to write the units. Otherwise, you will never realize you're going wrong. Okay. So what is state 2? State 2 is at 350 kilopascal, x equal to 0.75. So this is state 1. State 2. 350 kilopascal, h equal to question mark and x equal to 0.75. Okay, so let's go to saturated R134A data. This is the saturated R134A data. This is the saturated R134 data and this is the enthalpy entry, and we are looking at 350 kilopascal. In this particular thermodynamic table, there is no pressure entry for R134A. There is only temperature entry, but this appears to be very close to 350. No, this point.
Yes, sir. 350.
Yes, sir.
So let me just grab hold of this. let me grab hold of this. Okay, so let me get out my marker. We will have to do something between this and this. Okay, so and on top of that we have x equal to 0.75. So let us do this. So temperature 0, 5. Let us try to find out the enthalpy for 0.75 fraction. Okay, so at 0 degrees Celsius, what is the enthalpy at 0.75? It will be H of the fluid, which is 200. I'm directly writing down the values, but when you look at the recording once again, you will easily understand whatever I'm doing. Plus 0.75 times HFG. What is HFG? 198.36. It's the same way in which we did the interpolations for specific volume and specific internal energy. It is HF plus X HFG, nothing else. For 5 degrees Celsius, what is it? It's gonna be 206.75 plus 0.75 times 194.57. So, ladies and gentlemen, please tell me the values.
So the first one is 348.77.
348.77.
And next one is 352.6775.
677. I mean, you know, 2 decimal places. Now we're gonna say some. Let me also add. Okay, let me write it this way. H.75 is this. So we have H 0.75, 348.77, 352.67, pressure 294.0, 350.9, temperature 0.5, and we require the pressure to be 350. So corresponding to this will be H2, this will be T2. So let's do the calculation. How will we do it? We can do linear interpolation. So H2 minus 352.67 over 350 minus 350.9 is equal to 352.67 minus 348.77 over 350 minus 294.0. And if someone tells you, hey, I also need to know what the final temperature is, well, we can do T2 minus 5 over 5 minus 0 is equal to 350 minus 350.9 over 350.9 minus 294.0. We are just doing a linear interpolation between these values. Nothing sacrosanct about this. So what is the value of H2 using your calculators? Anyone?
So it's coming out 352.05.
352.05 kilojoule per kg, and temperature something between 0 and 5, and it's closer to 5, so it will be like something like 4.5 degrees Celsius, 4.8 or 4. Maybe 4.8. It's gonna be closer to 4.8, I guess. Hello?
So I didn't calculate the temperature. But so is there any need of temperature in this
There is no
equation?
need, but we should always, I mean, we are doing practice in class.
4.34.
We are doing practice in class, so it is always a fair thing to do. I mean, there's no harm. You cannot do. But what is it? 4.3. Someone said something.
4.34.
Okay, let's say this is correct. Let's assume this is correct. Okay, so now we have H1 and H2. H1 was over here. This was H1. This was H2. What was the total mass of R134A? 2 kilogram.
Yes,
So
sir.
Q12 will be 2 kilogram times H2, which is 352.05 minus 490 The units of this are kilojoule per kg and this unit is kg, so kg cancels. You finally get, what is this answer? These many kilojoules. What is this? Minus something. Minus of something will be there.
Minus 275.
So minus 275.9.
Minus 275.9 kilojoule. Okay, this is how you would do the problem. Let me tell you what I would do. I wouldn't call myself a same person, but let me show you how I would do it. I'd open this. I would go to options, preferences. I'll increase the font size for every one of you. I will say that P1 is 350, P1 is 100, P2 is 350, X2 is 0.75, H1 is equal to enthalpy of R134A, T equal to T1, P equal to P1. I will also say H2 is equal to enthalpy of R134A, P equal to P2 and X equal to X2. Then I will say that Q12 is equal to mass times H2 minus H1, and I will declare that mass equal to 2. I will simply press F2 and we get 274.8, 275.9, close enough. Okay, let's also see whether we have the correct state points. We have the correct state points or not. Okay, I've not fetched the values, so let me also fetch the values. So I want to know what T2 is as well. So I will say, apart from this, for my understanding, I will say T2 equal to temperature, R134A, P equal to P2 and X equal to X2. The temperature is 5.008 degrees Celsius. And we had obtained 4.34. These are all interpolation artifacts. Don't worry about it. This table is not going to be precise. This is going to be precise. And obviously, if I fetch the quality for the first state, what do you think I should get? The quality for the first state?
100.
100.
We should get 100. So let's do that. Let's show people who have not practiced it using this. But yeah, T equal to T1 and P equal to T1. So you get 100. Okay, is everyone convinced we're on the right path?
Yes, sir.
Yes, sir.
Let's do another problem. There is not enough time. We have 10 minutes. We have 10 minutes. Let's try to do yet another problem. See, more problems you encounter, you're in a better position. Okay, you're in a better position. I'll try to select something which does not have so many interpolations, but in the end you will end up with doing so many interpolations. Okay, let's do something simpler. And you will end up doing so many interpolations. There's nothing you can do about it. Not every property value will be corresponding to a data entry. You see, what in just the previous problem itself, we saw that yeah, you had to jump around quite a bit, no? And there is a chance that in that jumping around you might miss something. And that won't be a conceptual mistake. That will be what kind of mistake? What kind of mistake do you call those?
Silly mistake.
Silly mistakes. So we call them silly mistakes. So regardless of that, you get partial credit, if not no credit. Where are we? Yeah, I've pasted the problem. So the question is very simple and it just, I mean, you need to do such simple questions as well so that you get confidence in fetching properties from the tables. Find the missing properties and give the phase of the substance. So first question is steam T equal to 120, specific volume equal to 0.5. So they're asking U, P, X, and all these things. So steam 120, V equal to 0.5. Saili, are you there?
Yes, sir.
How do we go about it?
Uh,
Logically, what should you do first?
sir, logically we should draw a graph.
No, here
It's
that is not entirely needed. Graph is not
logically, like I think that since specific volume is less than 1, so it will be inside the dome.
No.
And
This is your, I mean, come on. You're assuming that specific volume at the vapor is 1. So this logical step would be, I mean, I'm just rephrasing what goes on in your head, but you assumed something. It may be correct, it may not be correct. You must first see that whether V under question is less than V of the gas phase or the vapor phase at 120 degrees Celsius. Is that what you wanted to say?
yes, sir.
So let's go. Right now we are at R134A. We need to go back to steam. Let us go back to steam. And what kind of entry is it? It's temperature entry. Oh. So we have saturated water, temperature entry is 120 degrees Celsius. 120 degrees Celsius. So what do you see at 120 degrees Celsius? What is the specific volume of vapor?
0.89.
0.8986.
Okay, so this I'll copy. So this is temperature, pressure, Vf, Vfg, Vg, and this is yes. So it means that this state is in the saturated dome, which means that I can write this V is equal to Vf plus X times Vfg, and this is 0.5 is equal to 0.001060 plus X times 0.89080. So what is the value of X that we obtained using this?
0.56, I guess.
0.56. Yeah, that looks okay. Now we have obtained what X is, and we have also answered what is the phase of the substance. What is the phase of the substance? It's in two phase. It's in two phase because liquid and vapor is coexisting at this point. So we say that it is at two phase. Okay. It's a mixture of liquid and vapor. Now what about the pressure?
So
Pressure is directly
198.5.
given.
So it is directly given. Very good. 198.5 kilopascal. And what about the internal energy? So we have to go back to the table. We will copy this.
1638.
Okay, let's see. So this is gonna be UF, UFG, UG. So U will be equal to UF plus X times UFG. This will be 503.48 plus 0.56 times 2025.76, and this entire thing will be in kilojoule per kg. So what is the value? 500 and what?
1637.
1637. Okay, so this is how you would do it, but this is important whether this is true. If it is yes, if it was no, then what would happen? You would look up the superheated tables. Okay, this looks like it would be in superheated, but it's 10 megapascal, so it's very nice values. But let's see. I mean, okay, we're out of time, but do one thing. You do these problems sometime. Okay, so we've come to the end of the time, stipulated time today, and we did some useful concepts, and also we